Triangulation, why optimize? Triangulation is a technique of locating a 3D point observed from a known baseline. This technique is used in many areas, such as surveying, astrometry, navigation, and of course in computer vision for applications like structure for motion and SLAM, where scene reconstruction plays an important role. In fact, triangulation as a technique has existed for much longer than computer vision. The first drawing illustrates that in year 263, a Chinese mathematician, Liu, used triangulation to estimate the height of a cliff. The second drawing illustrates that in 1625, a Swiss goldsmith, Zubler, used so-called measuring tables for triangulation. In computer vision, two-view triangulation means locating the 3D point given its projections in two views of known calibration and pose. In the ideal case, the two rays corresponding to the same point would intersect, and knowing the exact equations of the two rays, it's trivial to find this intersection. But in the real world, there is noise in the image and inaccuracies in the calibration and pose, so the two rays don't necessarily intersect. Okay, given a pair of skew rays, how do we find the 3D point? Well, that's the problem we address in two-view triangulation, and as you'll see in the next slide, the solution is non-trivial, even for just two views. So the current gold standard is the optimal method that finds the intersecting rays that minimize the reprojection cost. The same principle is also used in bundle adjustment. Most of the time, this cost is based on the image reprojection error, shown here as D0 and D1. The cost can be in either L1, L2, or infinity norm, which means the sum, the squared sum, or the maximum of the two errors. Hartley and Nister showed that the optimal solution can be obtained in closed form. Alternatively, we can minimize angular reprojection error. Compared to the image reprojection error, the angular reprojection error has the advantage that the optimal solution can be, it's much simpler and faster to compute. This was shown in our previous work. Another well-known method is the midpoint method that simply finds the midpoint of the common perpendicular of the two rays. Now, how do these methods compare? In terms of speed, both methods are quite fast, but the midpoint method is faster. The optimal methods achieve minimal 2D or angular reprojection error. On the other hand, the midpoint method produces large 2D error, especially at low parallax. At high parallax, both methods produce equally small 3D error. But at low parallax, the 3D error is larger for the optimal methods than for the midpoint method. In fact, this discrepancy between 2D and 3D accuracy was first reported by Hartley in the 90s. Now, with that in mind, our first contribution is that we propose an alternative midpoint method. The classic midpoint method finds the closest to a pair of points on each ray, and then from which the midpoint is extracted. And the depths of these 2 points are given by the equation here. Now, what we propose is to modify these depths like this. Notice that the only difference is in the numerator. When the rays intersect, this equation simply means the sine rule. And also, since we're using the magnitude of the vector instead of its projection onto the unit vector, our depths are always larger than the original ones. Now, we claim that our method is better at low parallax. First, consider the optimal method. The drawing here illustrates the solution space of the optimal method given a bounded reprojection error. As you can see, at high parallax, the blue points represent the ground truth, and the red points represent the worst case result. At high parallax, the 3D error is low. On the other hand, at low parallax, you can see that the worst case result is much worse. And this is because the point is located very far from the cameras. On average, this leads to large 3D error. In contrast, the midpoint method tends to locate the point too close to the cameras, and this, on average, leads to large 2D error. Now remember that in our method, the depths are always larger than the classic midpoint method. So this means that our midpoint is located farther than the classic midpoint, and this effectively lowers the 2D error. Also, since we are not minimizing the reprojection error, it doesn't send the point too far either. In short, we hit the sweet spot between the optimal and the midpoint method, achieving small 2D and 3D error at low parallax. Our second contribution is that we propose an alternative chirality check. In the classic midpoint method, inaccurate measurements can sometimes lead to negative depths. And when this happens, we can simply discard the point. On the other hand, in our method, the depths are always positive, so we cannot use the standard chirality check. So as an alternative, we propose to discard the point if assuming a negative depth brings the 2 points on each ray closer together. And this condition is given by the equation here. Our third contribution is the inverse depth weighting. In the case of unweighted midpoint, the reprojection error is larger for the camera with a smaller depth, as shown here by D0 and D1. Now, in order to compensate for this imbalance, we propose to use the inverse depth as a weight, so that we can bring the midpoint closer to the ray with a smaller depth. And the weighted midpoint is given by the modified equation here. For evaluation, we created a synthetic data set consisting of 4 different pose configurations as shown here. The point cloud is generated with a Gaussian radial distribution, and we vary the distance between the point cloud and the cameras from 0.5 to 64 times the baseline. We also vary the image noise level from 1 to 8 pixels. 8 pixels. In total, this provides over 1 million unique triangulation problems. And here's the result. This plot shows the 3D error across different parallax angles. The solid lines represent the optimal methods. The circular markers represent the classic midpoint method, and the X markers represent ours. As you can see, at parallax below 2 degrees, the classic midpoint and our methods outperform the optimal methods by a significant margin. And above 2 degrees, the performance gap gradually decreases, and above 4 degrees, all methods perform equally well in terms of 3D accuracy. The result is quite different for the 2D accuracy. For parallax angle below 4 degrees, the 2D error is significantly larger for the classic midpoint method. On the other hand, our methods are almost as good as the optimal methods. For larger parallax angle, compare the red and black X markers. They respectively represent our method with and without the weight. As you can see, our inverse depth weighting effectively lowers the 2D error, and this 2D error becomes similar to that of the L infinity optimal methods. As for the speed, the classic midpoint method is still the fastest. And our methods have the speed comparable to that of the state-of-the-art optimal methods. So in summary, our method is as fast as the state-of-the-art optimal methods, and it produces smaller 2D error than the classic midpoint method, although not minimal. At high parallax, all methods produce equally small 3D error, but at low parallax, classic midpoint method and our midpoint method produce much smaller 3D error than the optimal methods. So now back to our original question in the title, why optimize for triangulation? It's quite clear that for 2 views, simply minimizing the reprojection error doesn't automatically guarantee 3D accuracy. In particular, for parallax angle below 4 degrees, we recommend not to optimize, and instead we recommend to use our unweighted midpoint method. Although this method is not optimal in a geometrically meaningful way, it clearly outperforms the existing optimal and non-optimal methods at low parallax. Also, we recommend the unweighted version because the inverse depth weighting does not help much, at least at low parallax. For parallax angle above 4 degrees, we recommend to optimize, specifically using the L1 angular method. This method has a similar 3D accuracy to the rest, yet it's optimal in the L1 angular projection error and also is as fast as the classic midpoint method. Thank you for your attention.
Questions, please. There's one over there.
Thank you.
You're contrasting your method to other methods, saying that other methods optimize something, your method doesn't optimize. But can there be some interpretation in which your method is optimizing?
Actually, one of the reviewers made the same comment. And well, we're not claiming that our method is not, well, maybe it is optimizing something, but we couldn't find the geometrically meaningful error that is optimizing. And another thing is, yeah, I mean, you can optimize with respect to the 2D error, but there is no known method that optimizes with respect to the 3D error.
So maybe it has to do with the fact that distributions have actually complex shapes and things like that, right?
Yeah.
Oh, thanks.
More questions from this room? Any questions from the other room?
No, there are no questions.
No? Okay, well, thank you again very much. The second talk, or the third one in your list, is going to be given by Ravi Garg from the University of Adelaide, and it's called Single View Object Shape Reconstruction using Deep Shape Prior and Silhouette. Thank you.
Hello everyone. So I'm Ravi Garg, here to present our work on reconstructing object instance from a single silhouette using a learned deep shape prior. This is the work done by Kejie in collaboration with me, Ming, and Reid at the University of Adelaide. So the problem we are trying to solve is that of reconstructing instance of an object in full 3D from a single image, and our reconstruction includes occluded parts of the objects as well. So as it's evident and obvious to most of you, the recent state of art to solve this problem is relying on deep learning techniques. And essentially, the goal there is to learn a mapping function in the form of a neural network which can map this single instance of an image of an object to its full 3D reconstruction, generally in a canonical pose. However, supervising such a neural network is not an easy task because it demands that we have paired data set of instances where we have 2D image, which is real on one side, and the 3D object reconstruction, full 3D, of the same image. So in absence of such data set, which is very difficult to obtain, most of the methods do rely on synthetic data sets for learning. So essentially, we have a large catalog of man-made object shapes with fine details in data sets like ShapeNet. And most of the approach starts from taking these CAD models and rendering them with some random lighting condition and a random pose against some real image and create this 3D, 2D pair as a noted data set for training the shape predictor. As you can already see, that the rendered images have several issues. We have object placed out of context on a random background. We don't have consistent lighting in the rendering for background as well as foreground, have minimum clutter in the rendered instances, and pretty much no external occlusion, all of which is the case when we go to the real world scenario. So we are training our system in a simulation which is drastically different from reality, and that means that we are limited in terms of deploying our systems into real world. And most of the research in this field at the moment is happening in mitigating this domain gap. So one common solution most of the approaches go for is to use some 2D annotations which are relatively easier to obtain on real images. These 2D annotations can be a depth obtained from a commodity camera, or maybe a single object silhouette annotated by hand. So these methods mostly results on a stage-wise training procedure. First, you train two networks, one which predicts the shape for a single image, the object consisting in it, and the second one which predicts the pose in which the object is observed. Using these two predictions, then you can render the object and find out, for instance, a silhouette which you want to match with the annotated silhouette. And the whole set of encoders and decoders you see in this figure are then fine-tuned with these 2D annotations. And this gives us basically a system which, in our opinion, is still subpar reconstructions and pose estimations from the single image. Have various problems. So first, that the single view predictor, when run on two views of the same object, gives you inconsistent results. More importantly, it has been noticed that if you try to infer a segmentation mask with your pose estimator and shape estimator on most of the real images, the performance of this segmentation induced by the 3D reconstruction is subpar even to off-the-shelf semantic segmentation networks, which are actually trained without any 3D knowledge of the object shapes. So noticing this performance gap in segmentation, many recent approaches such as MARNet or object-centric photometric bundle adjustment try to use an off-the-shelf silhouette extractor, a simple neural network like, for instance, DeepLab, which gives you the silhouette for an object given an instance, and try and optimize for the latent code which can generate a shape, and pose, which then will give us a silhouette which is much more consistent than whatever the single view segmentation scheme is providing us. So if you do it naively, what happens is that you're going to overfit to a lot of noises which any single view segmentation scheme is going to be having, and bake all these segmentation errors in to your reconstruction as well. In this talk, what I am focusing on is to address two problems. One, that given a noisy image silhouette, how would you actually use the scheme to optimize for a latent code and pose together? And more importantly, the second question, which is that if we had to resort to and rely completely upon the single view semantic segmentation prediction, why actually learn image to object shape mapping function on synthetic data sets and fine-tune it and then rely on refinement at all? So to answer these two questions, we look into the literature. Pre-deep learning, this problem was indeed solved in a traditional geometric way, where methods which were trying to use a shape prior to do 3D reconstruction from a single silhouette were prevalent. So these methods had a simple training scheme in which a whole bunch of object shapes were embedded into a low-dimensional space, a latent space, using techniques like GPLVM. This gives this approach a way to generate any particular 3D shape, so one of these cars, for instance, and then search this latent space to find out which point will give me a shape combined with the pose, which will be consistent or most consistent with my silhouette. But the success of this approach has actually relied on the probabilistic nature of the learned latent space. So as you can see in this figure, this 2D latent space encoding all the car shapes, every point in the latent space is associated with a learned prior probability. What this prior probability is telling us is how likely it is that if I use my generative function at that particular location in the latent space, I am going to reconstruct a shape which is car-like. So you have lots and lots of area in your latent space from where you can do the generation, but you don't generate something which looks like a car or your training examples. And this restriction of the search space to only feasible car-like shapes was essentially the key which these methods rely on. And what we want to do is to replicate the same thing, but replace the traditional dimensionality reduction methods like GPLVM or kernel PCA or some variant of those with deep learning. So essentially, our approach is very simple. It has two training steps. In the very first step, we train an autoencoder. It's a point cloud autoencoder. It takes 3D point cloud as the input. Encoder encodes it, creates a latent representation for it, which is a small dimensional representation. And then the decoder then can act as a generative function which can map any point in the latent space to a 3D structure. And this point cloud autoencoder is trained using chamfer loss in general. Now this decoder, although can act as a generative model, the key here is to make our latent space probabilistic or probabilistically meaningful. So essentially, what we do in the second step of training is go through the whole bunch of 3D models we have, extract the point cloud, pass it through the encoder which we have learned using autoencoder, and create a set of latent codes for all the training instances of object class we have. And then we fit a mixture of Gaussian to this latent code. So typically for object class like chair, 5 mixture models are sufficient in our opinion. And we use EM algorithm to estimate the mean and the variance of our Gaussian mixture model. What does it give you is that if you ask a question that here is a latent location of, say, a 256-dimensional vector, what is the likelihood that if I use my decoder function, I am going to generate something which is a likely object shape, which is more chair-like shape. And we use this probabilities, the prior probabilities, the same way as traditional approach use at the inference time in the following way. Imagine you have a real image. You use any of the shelf segmentation network of your choice. So we use here Deep Lab to predict foreground-background segmentation of our object of interest, and we sample some 2D points on it. On the other hand, now our task at the test time is to search this latent space for a latent location which can generate a 3D reconstruction, and we also need to optimize for the pose, which when combined with this 3D shape can give us the projected 2D points which are in line with the sample 2D points from the silhouette which we are observing. So of course, it's just simple semantic segmentation consistency term. And in the point cloud representation, you can minimize basically 2D chamfer loss on the projected points and the sample points. But along the way, what we don't want to do is to drift away to the various locations we are going to have in our latent space, which are completely not meaningful, meaning they have very low probability or likelihood to generate the object of class that we are interested in this case, a chair. So we basically want to do that, and we do that by restricting our search space. Effectively, we are trying to minimize the log likelihood of our GMM with respect to the latent code that we are trying to find out. And at the inference time, all you rely on is a single off-the-shelf deep lab-like silhouette estimation and optimization approach, which can use the shape prior. The result of this approach, which is pretty simple approach, is evaluated on realistic dataset Pix3D, which has real images of diverse shape like chairs, sofa, or table, and corresponding 3D shapes, which are aligned with them. And we compare against a whole lot of landmark approaches which solve the same problem. These approaches use different representation, point cloud, volumetric representation, or even meshes, have very sophisticated encoder-decoder architecture replacing the other ones for generating a good single view shape estimator. But common to all of these approaches which you see in the table is a synthetic pre-training step where you're training everything, and then fine-tuning it with some kind of weak annotation. And some of these approaches, like MarNet or Pix3D, even use the refinement to fit two off-the-shelf silhouette. However, in contrast, our approach just simply learns an autoencoder, fit a Gaussian mixture model to it, and no further training is required. In fact, we don't have any single instance where we have a 3D object structure paired with a 2D image, neither synthetic nor real. Here are some qualitative comparison which shows the benefit of our approach, how well can our approach cope with various noises you're going to have in generating object silhouettes. So when you use any classical segmentation method, for first instance, for instance, the background chair is confused with the foreground one, and in the last instance, the floor is leaking into the chair, having gross error in the semantic segmentation. But we still generate very plausible object shapes, whereas other methods which are doing the refinement using single silhouette are all overfitting to the noise which is present in the silhouette. Here is some more instances of our 3D reconstruction visualized from different views. But the more important thing here, which I want to tell, is that we show through our abolition study how important actually learning a probabilistic prior and using it appropriately is in the context of 3D reconstruction. So we do that by dropping basically our log likelihood term, which I was talking about, and create a baseline which only relies on silhouette consistency. And of course, this results into gross overfitting, as you can see in this instance, to a terrible mask a single view object segmentation network can give you. Whereas if you use the prior along with the silhouette consistency, you generate only plausible chairs. And even when most of the object is not segmented, as in the first instance, you generate something which looks much more meaningful and closer to ground truth. Of course, you can, like any autoencoder, interpolate and explore the latent space. And you can see here that what I am doing is linear interpolation between three means of the Gaussian which I have learned. And focusing on the instances between mean 1 and mean 2, for example, of course, the latent space is capable of generating some weird hybrid shape between a stool-like chair and a rolling chair. These are, however, we know, are very low likelihood locations in the latent space. And you can see on the bar that the likelihood of these points are very low. And this is the key, which helps us not overfitting to the silhouette, but be able to do reconstruction properly. So in summary, what we propose here is to rethink the role of deep learning for single view object reconstruction. We question whether we want to learn an end-to-end network which can map a real image into the corresponding 3D object shape, or do we not need it at all? And our experiment suggests that we can get close to state-of-art result without any training of this model, and without resorting to rendering sort of hundreds of thousands of pairs of instances which correspond to image and 3D shape. So the take-home message from this work essentially is that when you're trying to solve a vision problem and creating a pipeline, and you want to use deep learning, maybe you want to take a step back and think about which pipeline to use, first of all, and which portion of the pipeline should be left to traditional geometry and optimization, and where learning can help. Thank you.
Right. Questions for Ravi? Yes, there you go.
Thanks for the talk, and I like the slide where you're interpolating between the different means. If you could just flip to that one a moment.
Yeah.
Oh. Or not.
Can you go back to...
Yeah.
So one thing I noticed was that the means are very nice and sharp. So they've got like sharp legs on the chair, and as you interpolate, they get very fuzzy before kind of going back again. I was wondering if you could comment on that, and if there are ways you think that this fuzziness could be reduced, so it's more sort of realistic shape chairs between the means.
So we did some initial experiments replacing, for instance, the autoencoder with variants, VAE, for example, which actually do have a prior, or GANs or other stuff. By the way, you should notice that the GMM is fitted to already pre-trained autoencoders. So that's where I'm coming from. But when you compare all these things, what we found is that it's very difficult to preserve all the diversity in the shape class like chair and not have any single point in the latent space where you're going to reconstruct some garbage hybrid. So the interpolation as you want it to work generally doesn't work that way. If you are trying to make it very nice, what happens is that you're going to lose out on a lot of details. So it's a compromise, but knowing the likelihood is very important because you can avoid those reasons in the latent space when you are doing optimization.
Okay, thanks.
Thank you. Any other questions here? Yes, one more there.
I'm just wondering, sorry, did you try any, so I noticed in your examples you've done chairs, and then there was also some with tables as well.
Yeah.
Did you actually train any multi-class, did you train at all with any, multiple classes? Just the reason I ask is because the encoder-decoder I see is at a point net that you use. Yeah, so I've always, whenever I've tried to use that, it's been terribly bad as soon as you have multiple classes, so chairs, tables, and something. And I was just wondering if your method actually aided that at all.
So a detail which I did not mention, the autoencoder we train is on 13 classes of ShapeNet, a single autoencoder. So it's a single point net autoencoder, and it encodes all 13 classes. However, the prior, which we are learning, is class-specific. So by the time you do segmentation, you eventually know what object you have, and you can use this information already. So this point net is trained on all classes, but the parameters of GMM, which are very few, right? 4 or 5 Gaussian mixtures are per class, if that answers your question. So in this case, it works fine for 13 classes.
All right, so perhaps we can take one question from the other room.
Hi, thanks for the good talk. I had a quick question. So in latent variable models, like the variational autoencoder, recent stuff has showed that when you learn the amortized posterior, it generates really good samples because you're basically finding the best posterior modularizing out the input data. So is there something with your fitting of the mixture of Gaussians that helps prevent overfitting, sort of, like that generates the same thing? Because the amortized posterior generates exactly the good-looking samples that I guess that you want. So is there something that's going on here that's different?
So we haven't really tested that kind of a scheme, but what I want to highlight here is that for the purpose of learning a good embedding space, you need two things. You just don't need to see what am I generating by randomly sampling the latent space. Maybe you can learn a latent space, as I was telling before, where you only reconstruct and generate good examples, which looks nice chairs. But how much of the variance in your training set can you preserve? So are you missing out on some details, or some of the instances are never reconstructed? So when you, what you're trying to do when you're trying to learn a latent space is always compromise between how well every point in the latent space can represent a chair and how many chairs can I represent, if it makes sense. So, so we found learning any kind of probabilistic representation on top of a simple autoencoder to be the best choice. We don't want to worry about the problem that our latent space can generate non-feasible chairs.
Okay, thanks.
Right, thank you very much for your talk. Our next speaker is Nitin Agarwal, and he's going to talk about learning embedding of 3D models with quadratic loss.
Just slightly dim the lights, if that's okay. Yeah, that should be okay. I hope you guys don't see. Okay, thank you for the introduction. Hi, I'm Nitin, and today I'll be talking about our work on Hi, I'm Nitin, and today I'll be talking about our work on Quadric Loss and how we can use it to reconstruct higher quality 3D models. So sharp features like edges and corners of 3D models are extremely important for human visual perception. It's extremely fascinating to see how our mind is able to infer the 3D shape of an object just from these features. So for example, I'm sure everyone in the room can guess that this image is of a coffee maker, or that this is a mechanical part. These properties are also exploited by artists who use these features for modeling purposes. And hence, in this work, we try to focus on how can we reconstruct 3D objects as well as preserve sharp features in our output 3D reconstruction. Current 3D reconstruction techniques heavily depend on the input 3D representation. So for example, images or voxels, although are flexible and friendly to learning, can be difficult to geometrically manipulate or represent high resolution meshes. Part-based models, although overcome some of these shortcomings, are basically not friendly for learning. Point and mesh representations have recently gained a lot of popularity because of their numerous benefits, such as being lightweight, flexible, they can represent high resolution models, and they are also friendly to learning. And hence, in this work, we primarily focus on these two representations, namely points and meshes, and propose a new loss function which they can use for reconstruction. But before talking about our loss function, let's briefly analyze and see what current loss functions are available today, particularly for point and mesh networks for 3D reconstruction. And briefly, they can be categorized into two. One being the point-based, in which which basically try to compute a dissimilarity between two point set distributions. And the other is a point-to-surface-based loss functions, which try to minimize the distance between the output points or the reconstructed points and the input surface. Let's look at some examples for each one of them. L1 or L2 loss is perhaps the most common point-based loss function. It requires one-to-one correspondences and the cardinality of the point sets to be the same. It then computes the Euclidean or absolute distance between the point sets. Earth mover's distance is similar to L2 in the sense that it requires the cardinality of the point sets to be the same. However, it then solves an optimization problem where it computes a bijection between the point sets. This step is usually quite expensive and often approximated. Chamfer's distance is perhaps the current standard for 3D reconstruction tasks. It does not require one-to-one correspondences, nor does it require the cardinality of the point sets to be the same. It simply sums the nearest neighbor distance for each point to the nearest point in the other point set. Chamfer's distance works really well in recovering the overall structure of the 3D object. However, it does not preserve the sharp features and can often result in collapse of small structures, as you can see over there. This is because it can be minimized by assigning just a single point from one point set to a cluster of points in the other point set. Coming to point-to-surface-based loss functions, surface loss tries to minimize the point-to-triangle distance. So here, S is an output point, and T is its corresponding point in the input mesh. dt computes the shortest distance between S and the triangle faces. Surface loss is then computed from S as the minimum of these point-to-triangle distances. Note, as this is a point-to-triangle distance, one needs to take care of all the 7 cases, as the point which minimizes this distance could lie on the 3 edges of the triangle, or the 3 vertices, or even inside the triangle. Edge loss is similar to surface loss, but instead of point-to-triangle, it minimizes the point-to-edge distance. However, as you can imagine, one needs to first manually annotate all these edges before computing this loss function. Instead of minimizing distances, normal loss minimizes inner product. Essentially, it requires edges between the output point S and the neighbors of its corresponding input point T to be orthogonal to the normal plane, to be orthogonal to the normal vector. in our contribution in this work is that we propose a new point-to-surface-based loss function called Quadric Loss, which minimizes the displacement of points in the normal direction, thereby preserving sharp features in the output reconstruction, as you can see here, for these mechanical paths. While other losses do not care about sharp features and focus on either the overall shape or the point distribution, our Quadric Loss is specifically focused to capture sharp features in the input mesh. Now, Quadric Loss was inspired from quadric error, which was first introduced for mesh simplification back in the late 90s. Essentially, the idea is to reduce the polygon count in a mesh while retaining as much sharp features as possible in the input mesh. Quadric error was used to identify these sharp features which were maintained during simplification. So what is quadric error? As the name suggests, it's the square of the distance between the point S, represented as homogeneous coordinates, and the plane P with having a unit normal vector. So given P and S, quadric error can be written as the square of P transpose S, which simplifies to S transpose times Q times S. Where Q is called the quadric matrix, it's a square symmetric matrix determined only by the plane P and not by any points on it. Note, quadric error for any point on the plane, like here I'm showing you T, will be 0 as it lies on the plane. We can further extend this concept to multiple planes where the quadric error between S and the planes P here, which are incident on T in this figure, is computed by first summing the quadric matrices of all the planes and then computing the quadric error just as before. Note the quadric error of T will be 0 as it lies on all the planes P1 through P7. Now, borrowing concepts from simplification and quadric error, we define quadric loss between the reconstructed point clouds S2 and the input surface M1 as the sum of quadric error of all the points in S2. Note, to compute quadric loss, one just needs to know the quadric matrices of the input vertices. Now, quadric loss can be computed in several ways. The first and perhaps most obvious is to just iterate over all the points in a mesh and all the meshes in your batch. Obviously, this is not efficient. The second is to compute the loss on all the points in a mesh together. This would construct a square matrix, and it's not difficult to see that the quadric loss would be the trace of this matrix. This is also not efficient. As you can imagine, this matrix is of dimensions n square. As n scales, this matrix would not even fit in your GPU memory. The third option, which is what we do, is to first compute the outer product of S and reshape it. And then we can simply compute the dot product of S of the dot product with Q and sum all the values to get the quadric loss for a single mesh. This is fast, efficient, and can be easily performed from multiple meshes in your batch. Now, quadric loss has nice geometric interpretation as well. The ISO value surface of quadric loss represents a family of ellipsoids for which one of the three axes represents the normal vector and the length of the other two is inversely proportional to the curvature of the point. So what I mean by this is, on planar regions, the ISO surface would be like a disk here, meaning the reconstructed point can lie anywhere on the plane, but any displacement in the normal direction would induce more quadric error. Similarly, on edges, the reconstructed point can lie anywhere on the edge, but any displacement away from the edge would induce again more quadric error. And similar arguments can be deduced for points on corners as well. In comparison, chamfers or L2, they behave more like spherical losses where equidistant points have equal error. Hence, to summarize quadric loss, it preserves sharp features by minimizing displacement of points in the normal direction. It does not require any manual annotations like the edge loss. It's fast, differentiable, and easy to optimize. Now, although quadric loss can be used for many reconstruction tasks, we test it on the task of 3D reconstruction using an autoencoder architecture and analyze the reconstruction quality. Specifically, we use the encoder from the dynamic graph CNN paper and the decoder from AtlasNet. For datasets, we randomly sampled 8,000 models from the ABC dataset, which was released this year in CVPR, which contains mechanical parts with sharp edges and corners. Keeping this architecture and all the hyperparameters the same, we analyzed the effect of various loss functions on the output reconstruction by measuring chamfers and metro error. So for those of you who are not familiar with metro error, it's just basically a metric to compare two meshes. So you just sample points on the meshes and then compute a Hausdorff distance between the two meshes. So lower is better for both of them. We first study the effect of these losses individually. As you can see, while normal loss focuses on higher order features, surface loss as you can see, while normal loss focuses on high order features, surface and chamfers on overall structure and point distribution, our quadric loss specifically encourages points to lie along the sharp features. And this is why it has a higher chamfers error as compared to chamfers loss. It's also interesting to see similar metro error for both of these, suggesting that the surfaces generated from both chamfers and quadric are similar. Next, we add chamfers loss to the surface-based loss functions and see the reconstruction quality. We saw most improvement when chamfers is added to quadric, suggesting this is because while quadric preserves sharp features, chamfers focuses on the point distribution. Now, although quantitatively the improvement is small, qualitatively the difference is quite perceivable. Here are some more qualitative results on when chamfers is combined with surface loss functions. As you can see, the combination of chamfers and quadric performs best even with shapes with different topology and geometry. The reconstructions are just much sharper with our loss function. We also tested quadric with more complex models like shapes from ModelNet 40 dataset and specifically tested in 3 categories and found consistent performance. Now, one of the limitations of quadric loss is that as it's an ellipsoidal loss, it cannot preserve the input point distribution, meaning that points on planar regions can lie, the reconstructed points on planar regions can lie outside the shape. And as you can see here, the points on the top and bottom of the cylinder, they're on the plane, but they're outside the shape. This can be easily corrected by adding L2 spherical losses, such as chamfers or L2, which preserve point distribution. So to conclude, in this work, we propose quadric loss, which is a new point-to-surface-based loss function, which preserves sharp features as it penalizes displacement of points in the normal direction. It's fast, differentiable, and easy to optimize. And it can be used for any mesh or point-based networks. Now, although quadric loss in practice performs quite well, it's just a step towards reconstructing high-fidelity meshes just as this. Thank you for your attention, and do come by my poster 164 to check out more results and discussion. And the code is publicly available, so do try quadric loss for your reconstruction problems.
Question? Anyone? There you go.
So with the combination of chamfer and quadric loss, how do you choose the relative trade-off between them?
So what we found in our experiments is you can weight those functions accordingly depending on what you choose more. Even with low chamfers and high quadric, we found good reconstruction results. As in, the reconstruction were much sharper just compared with chamfers alone.
Is it quite sensitive for how you tune it, or is it fairly easy to tune?
It's fairly easy to tune it. That's what in our numerous experiments we found.
So you're matching the points to the mesh surface then. What I was wondering is it sort of limited then by how good the mesh is? So I'm just thinking in slightly more complex point cloud environments where it's be captured by like photogrammetry or terrestrial laser scanner or something. So one of the problems we have is almost when you mesh, the meshing is quite poor, which is one of the advantages of something like chamfer, I would have thought. I was just wondering what your thoughts are on that.
So one thing probably I didn't mention is for all the losses in this work, we are using the correspondences from chamfers, which are not bijective. So I'm not projecting any output points on the input mesh. I am just using chamfers correspondences to compute correspondences like output point, which output point corresponds to which input point, and using that correspondences for the loss functions, for all three loss functions.
Okay, so maybe I've not understood something. So the plane, though, where does the plane come from? Is that estimated from the points, or is that from?
That's from the initial mesh.
Right. So what I was wondering is your loss function then limited by the quality of the meshing algorithm from the point, assuming that we haven't just got a model, we've actually taken something that was originally a point cloud, so it was captured as a point cloud.
Okay, I see what you're saying. So generally, in most of the deep learning frameworks is you have a good 3D model to begin with, in which your triangulation is nice, your details are nicely preserved. In cases in which you're scanning and have a scan point cloud and then performing 3D reconstruction, doing BPA or Poisson reconstruction, yes, it would depend on how the planes or how the triangles are. That would determine, obviously, the quadric planes, and it would affect the quadric loss. But usually the assumption is you have good 3D models to begin with, right, and then you're trying to do some kind of single view reconstruction or embeddings or some stuff like that. So with keeping that assumption in mind, this works nicely.
Okay, thank you very much.
Right, is there a question from the other room? Is there a question from the other room?
There are no questions here.
No? Right. Thank you very much again for your talk. Right, next we have Roman Klokov from INRIA, probabilistic reconstruction networks for 3D shape inference from a single image.
So, hello everyone, thanks for the introduction, and I'm here today to present our work on a single image 3D reconstruction. So let's start by formulating the task. So what we want is to obtain a model which will predict a 3D shape given a single RGB image obtained from an arbitrary viewpoint. This problem got a lot of attention in the past 3 years due to its ill-posed, challenging nature. And models that try to solve this task usually face a lot of non-obvious design choices, which we will try to discuss just from this simple schematic overview of the task. So one of the hottest topics in this problem is the choice of 3D shape representation suitable for the task. As we know, traditionally, raw shapes are represented as mesh grids, but until recently, it was not that simple to use those in network neural network environments. So people came up with lots of different representations approximating those initial mesh grids, like voxel grids, point clouds, and so on. And actually, a lot of newly reported works continue to push the state-of-the-art in this task by using more and more sophisticated approximations of meshes. So another aspect of the task is the choice of the image conditioning mechanism in the model. As you will see further, it's not something which is always predefined for any model. Finally, there's the model itself, which combines all the things. Here, except for the standard choice of the neural network architectures, which in that case is heavily dependent on the choice of 3D shape representation, we also have a question of how do we learn these models. And normally, people tend to treat this task as in a completely supervised manner. By first extracting some features from the images and then trying to regress shapes directly from those features. However, there is another possibility, and what we could do is to treat this as a conditional generative task. In this, as we know, single image is a very limited source of information for 3D shape reconstructions. So actually, final reconstructions rely heavily on the model ability to imagine the missing parts. So, and as you can see, this is more close to a generative approach rather than a supervised one. So in our work, we took one of the first and the most basic representations, which is 32 cube voxel grids, and tried to focus on other aspects of the task. And we contribute probabilistic formalization of the task, of the single image 3D reconstruction task. Using this probabilistic formalism, we try to analyze different options for image conditioning mechanisms and training procedures. And this unified model allows for a fair comparison of all these different options. So let's talk about this formalism for a little bit. So here we assume firstly that our voxels are factorized over individual cell occupancies. So in the end, what we want to obtain, to predict, is the parameters of Bernoulli distributions for individual cell grids given an image. And then we use the intuition that although images and shapes live in two different domains, we know that they both come from the underlying 3D objects. So we assume that there exists a low-dimensional latent representation of this shape space, which we can use to define our probabilistic model. So this probabilistic model consists of two parts. First is image conditioned latent variable prior, and the second is latent variable decoder, which obtains the final reconstructions. Note that actually this model is independent of the outputs and inputs, and it could be used with other representations as well. So we can further extend our model to a family of latent variables models by considering partial image conditioning in the components. So here in the first line, what we did is we discarded image conditioning in the decoder, which corresponds to the assumption that I and V is conditionally independent given latent variable. And the second option is to get rid of the conditioning in the prior. In that case, it corresponds to the assumption of Z and I being a priori independent. Now, to train these models, we also can consider two options. The first option is to use Monte Carlo approximation of the likelihood, where we take the samples from this image conditioned prior. Another option is to follow the variational autoencoder framework and to introduce a variational lower bound for the likelihood, which takes this form. Here we introduced Q psi, which is a variational posterior, which depends now on not only on the image but on the shape of the object. So in the end, when we will optimize this using Monte Carlo again, we will now sample from this shape-dependent posterior. In other words, what is happening is that now we have explicit latent shape space modeling performed in an autoencoder manner. So another possible extension to this model stems from the consideration of both unconditional generative model and image conditioned reconstruction one. So if we now write lower bounds for both of these models, we can see that if we drop the image conditioning in the decoder and posterior and share the parameters of decoder and posterior between unconditional and image conditioned models, we can write a joint objective, a training objective, in which we actually introduce an additional unconditional prior p kappa. This unconditional prior during training will additionally regularize our shape space, while during training, during testing, it will allow us to sample from our model unconditionally. So practically, we developed an implementation of the proposed formalism, which we called probabilistic reconstruction networks. Here at the top of this scheme, you can see image conditioned prior, which takes the form of two-dimensional CNN, while on the right and left of the scheme, you can see posterior and decoder, which takes the form of 3D CNNs. Unconditioned prior is represented by a set of trainable distribution parameters, and we model the latent space with Gaussian distributions. Additional image conditioning is performed in a film-like fashion in our work. So during training, the model optionally use shape-informed posterior, while during testing it reconstructs the objects directly from the images in a deterministic manner by taking the mean of the latent space Z, latent variable Z. So to evaluate all the options, we took ShapeNet dataset and compute intersection over union metric for two thresholds, visualization thresholds, neutral 0.5 and slightly overestimating 0.4. So here in the first three lines, you can see the results of different image conditioning options trained with Monte Carlo. And as you can see, in that case, additional image conditioning improved the result. Interestingly, when we switch to variational training, we obtain that the simplest image conditioning option through the prior gives the best performance. This is a bit counterintuitive, but we believe that this happens because in the Monte Carlo case, this additional image conditioning actually compensate this inefficient sampling from image conditioned prior, while here we have a posterior which is conditioned on the full shape information, and we don't actually need this additional image conditioning because it just leads to overfitting of the model. We also compared our best result to the deterministic case of the same model, and as you can see, the results are worse, which suggests that using stochasticity really helps for this kind of task. As for the joint generative approach, which is the last line, unfortunately the results are slightly worse, but at practically no cost, you are now able to sample unconditionally from the same model which does the reconstruction. To compare with the state of the art, we also computed point-based metrics, chamfer distance and earth movers distance. And as you can see, our approach significantly outperform all voxel-based previous baselines. And interestingly, even for point-based results, we managed to obtain state-of-the-art and earth movers distance and like the second result for chamfer distance. And that's even though other approaches use more sophisticated shape representations and directly optimize for those metrics. We also performed some visual comparisons of our worst model, best model, and the version of the best model, which is deterministic. So here you can see 4 examples where our variational model works best, and 1 example where it is the worst. Our code, well, in general, you can see that variational model gives better details. Our code is available online, and thank you for your attention. I will be happy to answer your questions.
Questions, Roman? Yes, there's one there.
Perhaps a silly question. So in the results you show, there's a chosen orientation of the grid of the 32 by 32 by 32 voxels. How is that orientation chosen?
Here, well, the model here actually works with, we always predict the canonical pose. So the input images could be from arbitrary poses, but the prediction is always in canonical pose. And here it's just for illustration purposes. We just, like, we took some pose and applied it to all the pose which comes from the image and applied it to the reconstructions.
So you get a canonical pose
in model, yes.
In a separate process.
First of all, the model predicts the canonical pose. Here, yes, we rotated the reconstructions to fit the images.
Would the aspect of the results change a lot with a different pose?
Yes, that's a good question. We checked that, and it seems that there's not that much variability in the result with respect to different views.
Thank you.
You're welcome.
Is there a question from the other room?
No, there isn't.
Okay. Right, thank you very much for your talk. The final talk in this session is by Ivan Eichhardt, optimal multi-view correction of local affine frames.
Thank you. So I'm Ivan Eichhardt from Hungary. It's an honor to be here and present you our joint work with Daniel Barat, optimal multi-view correction of local affine frames. So this work is related to feature-based vision, where you have images and somehow corresponding regions or features are extracted, and then we solve some kind of geometric task. So if you have only the region centers, you have point correspondences, and you can use the point coordinates to then solve geometric tasks. But it turns out that the underlying shape of the regions are also useful and meaningful geometrically. Shape of this region is called the local affine frame, which is basically an oriented ellipse. And the pair of local affine frames form a so-called affine correspondence. So why use affine correspondences? They have powerful results in image matching, in challenging conditions, and also in surface normal estimation, where a single correspondence can be used to determine surface normal, just like triangulation. And also a single correspondence can be used for homography estimation. In this figure, you can see a multiplane segmentation of a scene using a pair of images. Different colors denote different planar segments, different homographies. And two correspondences are enough to estimate the relative pose between two views, where you would need 5 point correspondences to solve the same task. So that turns out for robust estimation, that means fewer iterations, for example, in RANSAC. If you consider this figure on the right, then on the horizontal axis you see the number of correspondences we have, and on the vertical axis the number of iterations basically that RANSAC would take to perform the estimation. So if you take only 2 samples in each iteration, you will need way less iterations for RANSAC to perform the estimation. That's the red curve there. So affine correspondences have applications and works related to fundamental matrix estimation, homography estimation, pose estimation, and so on. And just to highlight some recent works which consider multiple view correspondences, affine correspondences are related to surface normal estimation and structure from motion. And these are recent works. But what's the catch when using affine correspondences? Unfortunately, while the center of these regions are quite certain, their shapes are quite wobbly. So in a sense, they are more sensitive to noise. So if we could have somehow better affine shapes, we could potentially improve meshing and geometric inference. On the right-hand side, you can see two view tracks of local affine frames represented by ellipsoids. So how could we improve local affine frames? Our basic idea is that we somehow try to impose the multiple view constraints in a multiple view environment. On the right-hand side, you can see a figure, and you can almost feel that there must be some kind of relation between between views and the surface and the shape of the features. On the right-hand side, you can see a multiple view tracks of local affine frames. So some geometric background is the following related to affine correspondences. So if we have a point on a surface, the point is called S, and if we take its projections onto two views, we get a point correspondence from points x1 and x2. They are image points. If we take the Jacobian of the projection, we get 2 by 2 matrices J1 and J2. And actually, if we know these values, we can determine exactly the affine correspondence, which is the corresponding points x1 and x2, and the relative affine transformation, again at 2 by 2 matrix. But usually we don't know these values exactly. We can approximate using outputs of different feature extractors. So we can measure these features using MSER, ASIFT, Hessian affine, so feature extractors. The shape of the features will be denoted by M. So the next step, our question is, how could we determine constraints on affine shapes? Well, it turns out, as well as we can formulate epipolar constraints on corresponding points, considering fundamental matrix and epipolar lines, it turns out that the normals of the epipolar lines are related as such, former work showed, under this 2 by 2 transformation. And if you have more complicated camera models, you can have more complicated epipolar constraints on the affine correspondence. So our proposed approach is as follows. First of all, we need to reformulate our epipolar constraint, and we propose to use this form. M1 and M2 are the shapes of our features, and A and B are vector coefficients of the epipolar constraint. They come from previous work. The subindex 1, 2 means it's an epipolar constraint between the first and the second views. So this is how our features are related. So given a multiple view environment, we can impose on the shape of our features all the epipolar constraints we have, pairwise. So we have a lot of constraints on our shapes. So we can formulate then an optimization problem. So we have our measured affine shapes as the output of our feature extractors, M hat, set of pairwise correspondences, and pairwisely the epipolar geometry, like fundamental matrix, relative pose, and so on. And then we seek least squares optimal shapes, which satisfy this optimization problem. We minimize the least squares difference between the measured shapes stated to all the epipolar constraints we can cramp in there. So it turns out it has a simple linear solution. And this matrix expression comes where it has the detected affine frames, so the shape of the features there, the unknowns we want to optimize for, and using Lagrange multipliers we will able to add the epipolar constraints to our equations. So the solution is, again, quite simple, well and efficient. considering it can be performed using linear methods. Our evaluation considers 4 different cases. At first, we were curious how different feature extractors perform. So as on the horizontal axis, you can see we compared different feature extractors using an affine error. So how well do they reconstruct some kind of ground truth shape? Let's consider just one of them, because that's much simpler this way, Hessian affine. As you can see on the blue marker, it has a mean error around 0.3. And after our refinement, the yellow marker shows that we were able to have the error of this extractor. And there are similar trends for all the other extractors. We were able to improve their performance on the real-world experiments. Next up, we applied our method as a pre-processing step to surface normal estimation. On this figure, on the horizontal axis, you can see an angular error. That's the angular error of the estimated surface normal with respect to ground truth. On the left-hand side, you can see low errors, close to 0. The right-hand side, around 90 degrees, which is really bad. So our evaluation showed that for a small error like 5 degrees, we were able to increase the number of normals estimated to such low error by 20% and reduce by 15% the number of surface normals with really bad errors. And a similar experiment was performed for homography estimation. Here, the horizontal axis shows the quality of the homographies we considered. It's the inlier ratio, so how many correspondents satisfy the homography. A great inlier ratio around 1. For example, if we consider that, this figure shows that we were able to have a 6-fold increase in the number of homographies estimated from refined affine correspondences. And we could have similar improvements after applying our methods for different inlier ratios too. And the last application is the refinement and the refinement of motion estimation of a multi-camera rig. We considered different robust methods, and we were able to see a consistent improvement when using our refinement as a pre-processing step. So the multi-camera rig itself is calibrated, so there for a moment in time, for a frame, we can impose our epipolar constraints and solve the optimization tasks, so we have better features. Consider the same for the next frame, and then solve the relative pose estimation. And we were able to see that we have decreased iteration number, runtime, and errors, and increased inlier ratios. So, summarizing, the central message of our method is that, and our work is that we were able to show that affine correspondences are again quite useful and interesting, and using our method as a pre-processing step, we were able to improve on a number of applications. Our future work considers the robustification of our approach and applying it to structure for motion and SLAM. Source code is also available with examples and integration into a structure for motion system. And thank you for your attention.
Right. Questions, please, for Ivan. Mira.
If you could, you had a slide where you compared the different kinds of detector. So yeah, back that one there. So one of the interesting things there is that the difference of Gaussian's detector seems to get the lowest, one of the lowest initial affine errors, even though it's not an affine detector. But it doesn't say refined to be as good as some of them. Can you comment on that? Why? If it seems to have a better starting place, but doesn't end up, say, as good as the A-dog AF.
Well, of course, different feature extractors focus on different regions in images. So it's not a perfect comparison just by considering that. And the scale of the features which are extracted, for example, TBMR at the end can extract in our setup large regions. Then after refinement it has, for example, worst error because we don't have just yet robustification in our method. So it's not a clear comparison, but just to show the trend that we were able to improve on them.
Okay, thanks.
Thank you.
A quick question here. Nice talk. This data that you present here on the accuracy, how big was the evaluation data set and what was the resolution of these images?
Thank you for your question. We used the multiple view stereo data set of Zehao. We used all of the images at the highest resolution we had.
Okay, so that leads to the second part of the question. So I wonder whether this is resolution dependent and image quality dependent. So for example, maybe if you had noisy data from or blurred data or lower resolution data, whether these numbers would change, and maybe also you would observe a bigger improvement thanks to your method. I don't know if you've done any of this kind of experiments.
We have not performed, but of course on noisy images, feature extractors, especially fine ones, became more wobbly. So that would impose some worsening in the errors.
And you think your method of improvement would still work? I mean, is there a breaking point when actually all this linear combination that you presented could it worsen the result or will always improve?
Well, that's a great question, as we can have errors when having outliers, because it's just a least squares estimation. Still, the output would satisfy the epipolar constraints, so it would have zero epipolar error at least.
Thank you.
Right.
Nice one.
Is there a question from the other room?
Right. Nice one.
Is there a question from the other room?
No, not this time.
Nice one.
Is there a question from the other room?
No, not this time.
Nice one.
Is there from the other room? Ask again? Okay. Is there a question from the other room?
No.
No. After 4 times of asking. Right. Well, thank you very much for your talk, and thank you to everybody who spoke in this session.